Yes, good morning, Monitorama. This has been quite a morning, hasn't it? And quite an evening before. I actually managed to walk into an elevator at exactly the wrong moment last night. I discovered there's a protocol. It's very interesting. I survived, as you can see. Some anomalies, I guess, are easier to detect than others. So, anyway, getting right down to it, I guess, the talk that I want to do this morning, the 30 minutes, is on the subject of anomalies and alerts and how we can do better with them. I think that, I guess I could start off with an assertion that monitoring systems today probably could do better, and they should do better, and what I want to do is start a conversation about how that might happen. So what I want to do is sort of take this in 3 acts to begin with, I guess. Act number 1 is just sort of looking at this current state of the art with respect to alerting and monitoring and discovering anomalies. And then look at the pain that has ensued and do some analysis on the pain to see what we can do to potentially find some relief and then discuss some possibilities for relief. As a bonus, I got a use case at the end, but I'm not sure I'll have time for it. We'll see. Okay. So let's look at the now. This is sort of your typical workflow. It starts off with data coming in across a fire hose typically. There's an engine that does some analysis, and then there's an alert that's issued appropriately at the end, ideally anyway. I think one of the problems that occurs is in the middle. The issue is that when anomalies are detected, it's sort of part of the same atomic operation to issue an alert. And I think that those two things, the detection part and the action decision part, those need to be separated. So that's what we're going to talk about. As a result of this fact that the two are not separated, you end up effectively equating anomalies and alerts, which essentially means every time you detect an anomaly, you get an alert, and the alert's quality suffers as a result. So there are bad ideas, and then there are worse ideas. Taking your cat into your bathtub to give it a bath is probably a much worse idea, so we shouldn't be too hard on ourselves. Bad ideas can also be corrected. So moving right along, let's look at the pain that this equating anomalies and alerts can cause us. One area that's a problem, and I was yesterday's talks were great, and a lot of the talks raised the issue of alarm fatigue or alert fatigue. By the way, if I say alert or I say alarm in this talk, as far as I'm concerned, they're the same. You could differentiate them, but at least as far as this talk goes, they're the same. So let's look at alert fatigue and sort of the root causes behind it. Well, basically you can raise alerts under various circumstances. You can have a problem or not a problem, and then you can raise the alert or not raise the alert, depending, and the quality of the alert is kind of judged by the correlation between those two facts. So if you have a good situation, if you have a problem and you get an alert, that's good. If there's no problem and there's no alert, that's a true negative. That's what TN stands for there. There's a true negative, and that's good too. So true positives and true negatives are good. Bad is when you have a problem and you get an alert. No problem, excuse me. Bad is when you have no problem and you get an alert. That's a false positive. And that's otherwise known as noise, and that is certainly a major contributor to alert fatigue. The really ugly situation, though, is where you have a problem and the monitoring system doesn't tell you about it. That's the worst case. I mean, why do you have a system if it's missing things, right? So that's one way to sort of judge the quality of alerts and begin to understand where the pain comes from. So the sort of first thing to ask is, if you're going to stick with this notion of equating alarms with alerts, or alarms with anomalies, or alerts with anomalies, you're going to get alert fatigue, and you're also, the anomalies are going to be contributors to the alert fatigue. And that's a problem, because anomalies can be good anomalies. If you go to the racetrack and you win $2 million, that's an anomaly, right? But it's not worthy of an alert. So equating anomalies and alerts is a problem, and if you think about the sort of the basic nature of an anomaly, is that it's a probabilistically rare event. And once you recognize that, you can begin to answer the question of how many anomalies you really should expect, and therefore how many alerts you really should expect, right? So looking at just a simple sort of common probability density function. This is the Gaussian distribution, and you could think of it as a smooth histogram. I love the fact that histograms came up so much yesterday. It's very valuable to understand how the information that you're getting is distributed. And this is kind of a typical distribution. There are lots of other distributions, and everything I'm saying will apply equally well to other distributions, but just looking at this one, where the anomalies live is in the tails, right? And the question is what's the likelihood that you're going to see things in those tails? And in this particular graph, what we're showing is a possible, if you're looking, let's say, at a metric, just pick one metric, and you're looking at all the observations that you could see from that metric, then what the graph on the y-axis is showing is what the frequency is that you saw that particular observation, right? You can express the observation in the units of the metric, or if you want to normalize and be able to compare sort of apples to oranges, what you can do is normalize and express what you're seeing in values of the metric as values in terms of units of distance from the mean, numbers of standard deviations from the mean. And what this graph is just showing is what percentage of observations you should expect to see at various different stages or various different distances from the mean, right? So in the tail, if the tail is far enough out, the percentage really goes way down. And that's why it's called an anomaly. The anomalies live there, they're rare, and so they're unusual, right? So if you look at this, it's expressing a percentage of the total population of observations you've made. Well, taking a look at how many observations you might see, that's one thing that we don't lack for in monitoring, is we have sample sizes which are huge. The good news is you get statistical power. The bad news is that you get a lot of anomalies, which if you just go through some calculations, you'll see that if you take, for example, one metric, you're doing 1 minute observations, you'll get about 500,000 observations in a year, and you'll get about 1,440 observations in a day. That's for one metric. People were talking about monitoring systems that were managing millions of metrics. So the numbers really get large, right? With the length of the time series or the metric that you're managing, as well as the numbers of metrics. So in the case of CloudWatch, an EC2 has 14 metrics. So 14 times 1442, that's roughly 15,000 metrics a day, or 15,000 observations a day. So just looking back, looking at the, I gotta press that way, right? There. Taking the percentages that we showed in the earlier slide and applying them then to the total population, if you had 50,000 metrics, which is not a huge organization certainly, if you had 50,000 metrics, you'd have approximately 5,000 observations that are 4 standard deviations away from the mean, which would reasonably be called anomalies. So in a shot, you're getting this 5,000 a day. Okay, now maybe 50,000 is too large for you. If you were to have that and make it 2,500 metrics, then that number the 5,000 would be cut in half, and you get 2,500 observations that could reasonably be called anomalies. So anomalies are actually very plentiful. I'm just showing my work here, if you're interested. Also, any mathy presentation should probably have some Greek letters, so there they are. Enjoy. Okay, so next slide. What did I just do? I just turned something off? So the next slide, what it says is that anomalies are plentiful. Yes! These last few days have had a few anomalies, haven't they? Thank you, and recovery. Quick recovery. Most impressive, thank you. This group, I must say, I have to thank everybody who managed to make this happen. It's incredible, it really is. So anyway, this may motivate you to sort of break the equality. Anomalies and alerts, they shouldn't really be equal. So let's try to break that equality. Well, if you do that, then now you've got this pile of anomalies that we just discussed, right? Pile of anomalies. You've got to decide which ones that you want to alert on and which ones you don't want to alert on, and therein lies the rub. So another interesting point, I guess, just besides the fact that the little area where, the area where, in the tails, that's so full of anomalies that it's a mixture. Some are true positives, and some are false positives. And so, if you choose to just sort of take the easy way out and say, if it's an anomaly, I'll alert on it, well, you're going to get flooded. And if you start to back off and say, well, I'm just going to only alert on a subset of these, then you're risking a false negative, which is the absolute ugliest type of circumstance. So these trade-offs they have consequences and they can be dire. So, okay. How do you look for the needles in the haystack, so to speak, where the true positives are, and only alert on those? That's kind of the problem. So here's the statistical approach to answering that question. So let's just suppose that you had a supervised learning circumstance, perhaps, where you have been observing one metric for a long time, and you've kept track of when there was a problem and when there was not a problem, and you created two distributions. You put the observations of that metric into two piles, the pile where there was a problem, the pile where there wasn't a problem, and you've got the two distributions here. This particular metric you can see from the graph, the green side is the low side. So low values for this metric are generally good, high values are bad. So it could be something like CPU utilization, for example. But the point is that you've got these two distributions, and they both have their anomalies that live in the tails. There's the really, really bad anomalies that are way far at that end, and there's the good anomalies where are at this end. Those may be noteworthy, but where the problems are is where these two overlap. So one of the things you can do with a alarming strategy is say, okay, I see an alarm, or I see an observed value of the metric. It's this blue dot here. And I look at the difference in the probabilities that it's bad, that it represents a bad problem, or that there is a problem there, versus the probability that we're okay. And that difference is big, and the probability that we're okay is higher. So I could say, all right, I won't alert. And you could do the same thing on the other end. Okay? And that's a very good strategy. It works well. It actually, if you take a look, it works well for, the vast majority of observations that you would see. However, when you look in the center there, that's where the decision gets much harder, right? That's where the difference in the two probabilities begins to, approach zero. And as we saw before, in that little area, there are lots and lots of anomalies. So let's zoom into that area. What you can do inside of that area is you can certainly err in the direction of not alerting on one side and err in the direction of alerting on the other side. That's cool, but that does not get rid of the sort of the middle area, and there the decision is very hard, and you're making a very hard trade-off between having your head in the sand where you choose not to alarm, or crying wolf where you choose to alarm. And so the statistical aspect of trying to implement an alarming strategy doesn't cover all cases, essentially. And unfortunately, the cases, there's lots of them, and that's due to the nature of monitoring, which just has a lot of data. So you end up trying to make trade-offs, and the trade-offs are the ugly case where you issue, don't issue an alarm when there's a problem. That tends to be customer visible. The other case is where you're, issuing too much noise, and you're hurting your support folks and the ops people with too many false alarms. That trade-off is often made in favor of lots of false alarms. That's the way monitoring systems work today, for the most part. So the question is what to do about this. Where can we seek some relief? And in my opinion, I guess I'm anxious to talk to people about what you guys think about all this. This is sort of a proposition. Where I think the problem lies, the root cause, is there's not enough information from the statistics or from the quantitative models. There's not enough information to make the decision. So how do we solve that? Well, I have one word: context. You need more context. Well, what is context? Well, here we've got 2 pieces of pizza. They look pretty nice if you like pepperoni. I would happily eat either one of them, right? However, with context, choice becomes a little more obvious, right? That's the importance of context. That's one type of context. Another type of context just sort of has to do with just the whole phenomenon of parts, the sum of parts making a whole, and the whole is greater than the sum of the parts. This particular case, I've got a bunch of parts lying here. When I put context around it, what I get is a nice SUV that may have air conditioning, 4-wheel drive, and can go a long way in the desert. That's a lot more information. That's the kind of thing that context can provide. I just put this in at the last minute. This is our weather. And what's interesting about this is you see an interplay of context between how much sun you get and what the temperature is. Kind of an obvious piece of context, but without that, these wiggly lines wouldn't mean nearly as much. So let's look at a more sort of DevOps-esque example. This is an example of a time series. It's a plot of a time series. It has raw metric values, which are the black line. And this is a very fancy algorithm. It has 2 bands of normalcy, one that's based on multivariate models and the other that's based on univariate models. The multivariate model is much more accurate. It's an adaptive algorithm, so once it sees a change in what's normal, it adapts. So you can see all this happening here. We start off at one level, it jumps up to another level. For a while, the bands, it's outside of the bands, so it's anomalous, and then the bands adjust. Okay, that's without context. You notice I don't have any label for the y-axis. There's no other information that you have. So it's hard to know exactly what alerts to issue or not issue based on what you know from this. But if you start to add context, let's just suppose that what we're showing here is CPU utilization. That's all well and good. That's still almost not enough context. What you also may want to know is that this EC2 changed. Its instance type went from a large instance type to a smaller instance type. So that jump is expected. However, if you have an alarming strategy based on the anomalies, then you're going to get a bunch of false positives. And this isn't the fault of the statistics here, or the fault of the anomaly detection, or the algorithms that are determining the band's width, the normalcy band's width. It's really the fact that you need to have context. So let's take a look at another case. Here, if I label the y-axis response time, then what happens is, on the one side, I've got good response time. On the other side, the SLA is not met. So I'll get some alarms for a while, but then what's going to happen is the algorithm adjusts, and now I'm getting false negatives. So context is critical here. The question is how do you add it to in a monitoring system? So here's one approach to doing that. You start off with the basic strategy, which is fine and works, and there's no reason to disturb that. What we do is we add to it. So first of all, just looking at the strategy as it exists today, and in terms of what context is being applied, you get values, you can tag values, so that's a form of context. You can also associate values with metrics. You can associate metrics with servers. This is all good context, and most monitoring systems today readily do that, some in more fancy ways than others. And then there's the engine side of things, and the engines can be quite fancy. They can have very nice query languages. They can create new metrics from old metrics by combining them and transforming them and all kinds of things. But what happens typically is the step of doing all the analytic work and then making the decision what to do. That step is one atomic step, and then you end up with an alert. So I think I skipped ahead. Okay, so what I'm suggesting here is what we might do instead is separate the two steps. So the first step, you get the data in, you add whatever context you can on the fly, but then think of alerting, the analytics aspect of the engine, think of that as something that's just adding context to a semantic model that you're keeping of the thing that you're monitoring. And the semantic model could include all kinds of things. The next slide actually shows that. But the idea is, this isn't new art. This is just standard information modeling, nothing new. But the idea is to keep all of that you know about what you're seeing or what you're deriving from what you're seeing, no matter how fancy the analytic is or on what time scale it executes. It could be streaming mode, it could be events coming in, it could be something that you're looking at cost maybe once a month. No matter what you find out, no matter how you find it out, it goes into that semantic model. Okay? And here's all the kinds of things you can do. I won't spend a lot of time talking about it, but I think the key point from all of this is that a lot of the analytic work is done on different time frames. Some of it has to be done at sub-minute levels, perhaps. Some of it can be done and is best done week over week or month over month. Or in the case of credit card clearing that you're doing and you're worried about Black Friday, year over year. So all of these different time scales play into what you know about each thing that you're monitoring. So the next thing you do, this is just another example. This is an example that involves relationships. It's important to understand what dependency relationships exist, what containment relationships exist. This is all stuff that can go into the model, and there can be very, very different tools that all end up in the same place. And once you've got it all in the same place, then what you can do is apply the next phase, keep that separate. The next phase is sort of an action policy that makes the decision, knowing what we all know, of what to do. So what does an action policy look like? It typically has three pieces: a scope, which basically says what subset of all the things you're monitoring does it apply to, what kind of things do you want to test, what conditions you want to test, and then based on the outcome of those conditions, then you take action. So that's one piece of it. Another piece, this is an example, I guess, of just a policy, what it might look like, and you can see that it's defining a scope as being EC2s, and they have to be in production, and they have to be a member of a particular ASG. Some of the conditions are involving things like computed metrics, things like slowly changing attributes, such as the number of CPUs in the EC2. If it's changing instance type, that may change. It won't change as fast as CPU utilization, but it does change. And it's also got a notion of time and a notion of calendar. So all these things are part of the tests, and then you can decide to send an alert, and then you can also possibly close the loop by taking an action, automating some remedial action, if you have confidence in that remedial action. So that's sort of the engine side of it, and then the other side, which is something also that came up yesterday, was just what the alerts should look like, what should be in them. And they almost always have things like timestamps, severity, maybe the duration, but all these other factors will definitely serve to reduce mean time to repair. So those are alerts with context. So going back to the with and without context slide, this is the without context slide. The with context slide then has a semantic model included. It has an engine that has two distinct components that operate on their own cycles, whatever cycle is appropriate to the kinds of things that they do. And in the end, you get alerts that are fancier, that have more information in them. So this is what I think is a reasonable strategy to try to improve alert quality. So the big takeaways are I know you're all in suspense. Where so I just went. Well, that's the big punchline there. Basically, that equating anomalies and alerts is probably not a good idea. The idea is to add context, thereby getting better alerts. To add context, take the effort to create a semantic model, as much automated as possible, but with human interaction as well. And think of analytics and all the data science that you put into a monitoring system. Think of that as discovering just additional attributes. And finally, take the approach, separate the action decision from the data collection process. Okay. So the best monitoring is all the math, all the analytics, but you need context as well. So that's it. Thank you. What's next? Did I end early? I wasn't keeping track of time up here.
You have a few more minutes if you want to take a question.
Are there any questions? I guess if we have a couple of minutes. I worked a lot to get rid of slides, and I'm shocked that I quit early, but it's good.
How many times have you run across a model which you thought the probabilistic they are? Or to look at the good side and the bad side and not always do one thing but roll the dice?
Yeah, it's rare, I'll be honest with you. I mean, having supervised learning in monitoring context is not as widely available or widely feasible, I guess, is another model. Oh, I should repeat the question. The question was, how many times have I encountered situations where I have information about known goods, known bads, and can create the kind of distributions that you saw up there. And it happens. I mean, there are situations where it can occur, but it's not as frequent in monitoring as in other areas. I think one thing that I heard yesterday, which I think is increasingly a feature that's being built into monitoring systems, is for people to provide feedback when alerts occur. So if you're getting a flood of bad alerts, then you can get feedback about it. And that could be the basis for supervised learning. If that helps. Did that answer your question? Yeah. Yes, question over there. Hi.
How much work is building this semantic model in comparison with the amount of work you're already putting into collecting all of the data and creating appropriate rule sets to take action on it?
Okay, the question was how much work is it to create a semantic model? And I would say it's a substantial amount of work, and that's probably why it hasn't been done. I also think that the sources of information to populate the model are so disparate that also adds a layer of complication. That there are very many specialized tools out there that will discover applications, or tools that will discover network infrastructure, or tools that will discover, transactions in an application. All of those are different. The monitoring solutions tend to specialize in those areas, and they're silos. The actual exercise of defining a semantic model and the entities and the attributes that participate in it and the relationships that exist in it, I mean, that is actually not that hard. What's hard is getting it populated accurately, and then, of course, with the sorts of technologies that have, now populate the cloud universe, it's a lot more complicated. Things come and go. Things that used to be fixed are no longer fixed. There's a lot of different changes that are occurring in different cycles. So and also I think the technologies. I mean, you have technologies for storing time series data. You have technologies for indexing huge amounts of data that's simple. You have relational databases that are, that have constraints that they enforce, that kind of thing. All those different technologies don't play well together necessarily, so it's hard. And I think that's why it hasn't happened yet, but I think it has to happen. So, does that answer your question okay? Yeah. Okay, that's it, I guess.